Charles' law now. Take a look at this next one. Charles' law. What's up with Charles, okay? And not Charles on BMF. We're talking about Charles' law from the gas law, okay? So with Charles' law, and not BMF Charles, Charles is dealing with volume and temperature. That means there's a direct relationship. That means that if my volume increase, my temperature is going to increase. If my volume drops, my temperature is going to drop. So if my volume doubles, then my temperature is doubling. Okay? Yeah, I gotta keep it silly so y'all can digest this material in a fun way. If my volume gets cut in half, my temperature is gonna get cut in half. It's easy peasy, all right? Easy peasy. So that's why we say there's a direct relationship between these two variables while we keeping pressure constant. Now, here's the other thing too. Your temperature must be in Kelvin. And if it's not, you're going to add 273 to it, okay? So that means if I give you a temperature reading in degrees Celsius, you just have to add 273.15 or just 273 to the number to get your answer in Kelvin, okay? That's it. Now, let's take a look at this next problem. Again, we're dealing with Charles' law, okay? I'm going to give you all the formula for it, okay? Which is T1 times V2 equals T2 times V1. So think about TV in reference to Charles' law. Again, Charles' law. Put these on index cards, okay? Put them on index cards. Now, move on, Professor TK. Here we go. We got T1, T2, V1, V2. Thank you, Ashley. Thank you. So right here, let's read the problem. It says a medical lab stores 0.50 liters sample of specialized gas at room temperature, 293 Kelvin. To preserve it, they move it to a cryogenic cooler at 77 Kelvin. What is the new volume? All right, so let's go ahead and write these down. So T1, the first temperature was 293 Kelvin. But guess what? They moved it to a cooler environment, which was 77 Kelvin. So that temp dropped. You already know if the temperature drops, what is the volume going to do? The volume is also going to drop. Okay? Now, by what factor? Okay, let's Mickey Mouse this and reverse it, right? Meaning, if you see that this is 77, right? And this is almost 300. Or better yet, let's work with this number. If I say 300 versus, let's round off to 80, right? By what factor can we say that this increased by? 80 to 100. This is almost roughly 4 times the amount, right? So if this dropped by approximately a fourth, then guess what? That's also going to drop by a fourth, okay? I'm just trying to get y'all to visualize, those of you that cannot use a calculator, just round the numbers up to where you're looking at them from that standpoint. So if this was 300, and this, let's just round it out to 100. So if this is 300, and that's 100, this drops by a third. So if this drops by a third, that's going to drop by a third. Okay? Now, to make this make sense, okay, let's go ahead and plug in what's a third of 0.5. 0.17. That's going to be my predicted answer. Approximately, okay, I'm just going to put this over here, approximately 0.17, okay? Approximately. But in order to find that out for sure, let's plug in the formula for V2. V2 is equal to T2 times V1 divided by T1. All right, 77 Kelvin times 0.5 liters divided by 293 Kelvin. Again, get rid of your units that you don't need anymore. And now you've got 77 times 0.5 divided by 293, and you've got 0.13 liters. So that answer was close enough to what we predicted it would be using the actual numbers here. Okay? That's how we got that answer. All right. Now, y'all know we're going to do another one, right? Here we go. And again, to save us some time, I had already put the numbers in Kelvin, but you all know they may not do that. This next problem right here, again, we're still on Charles' law, okay? Let's go ahead and put down what we already know, all right? We're going to go ahead and plug in what we already know to make sure. It says a 10.0 milliliter syringe containing air at a room temperature of 22 degrees Celsius, which is 295 Kelvin, is accidentally left near a patient's skin. Warming the air to body temperature, 310 Kelvin. What is the new volume? All right. So for this particular problem right here, you are going to do what? Plug in what you know. Again, guys, if you ever forget the formula, just make sure, can y'all continue to write the formulas down, so that you will have access to them. When I say that, put them on index cards, okay? So that way you will know. See, T1, V2, T2, V1. That's your formula. You're looking for V2, so that's T2 times V1 divided by T1. Okay. Now, y'all know we're going to do a guesstimation, okay, of our answer, so that way we'll know if we're on the right track, okay? So here's what you've got. The temperature roughly, it increased just an insy-bincy bit, right? So because it went up just a little bit, the volume is going to go up just a little bit, okay? I'm just going to make a prediction that, of course, we know that the predicted answer is going to be greater than 10.0 milliliters. I'm going to say it's just going to go up roughly to about, I'm just going to say 13, okay? Just a little bit. It's not going to go up that much. So you've got your T2, 310 Kelvin. Your V1, 10.0 milliliters. Your T1, 295 Kelvin. Again, cancel out your K's because you don't need those anymore. And let's plug this into our calculator. All right, so here we go. We've got 310 times 10.0 divided by 295, and we get 10.5. See that? 10.5. So again, like I said before, it did not go up that much. Because see right here, 295 to 310 wasn't a lot. It was about 15, right? So same thing here. So our answer is actually 10.5 milliliters. All right? 10.5 milliliters. Now, we've got another example dealing with Charles' law. Now, with the combined gas law, this one again is simple, but here's what you've got to remember. The combined gas law deals with all three variables: pressure, temperature, and volume. So Everything is going to be used together. But here's the thing. They're going to give you, okay? They're going to give you at least 5 of the 6 variables, okay? 5 of your 6 variables. So you've got P1 times V1 divided by T1, which equals P2 times V2 divided by T2. Now, all you have to do is cross multiply. And that's what I'm going to do. I would never suggest you plug the numbers in a formula just like that. My recommendation is that you go ahead and cross multiply so that you can get one succinct formula that looks like this. P1 times V1 times T2. P2, V2, T1. So that means when you actually go in and solve this problem, it's like you're going to be given either these 3 numbers are going to be given or these 3 numbers are going to be given. But you're going to divide by the other variables, okay? That's how you do these types of problems. So either this one side is going to be given and you're just going to divide by the other 2 numbers, okay? That's how you should look at these examples. Now, with that being said, let's go back up here to the problem itself. And I'm going to go ahead and plug the numbers in here. But in this case, you should notice something about the temperature. The temperature is not given in Kelvin. And just FYI, degrees Celsius plus 273.15, or you could just say 273. A portable oxygen tank has a volume of 2.0 liters, right? 2.0 liters. Let's go ahead and write that down. We're going to fill in the blanks. A pressure of 150 atm and a temperature of 25 degrees Celsius. But let's add 273 to that number, all right? And we get 25. We get 295.15, okay, Kelvin. Now, P2. The helicopter climbs to a high altitude where the pressure is 0.7 atm and the temperature is 5 degrees Celsius. Woo-wee! So we know it's hella cold. So that's going to give you 278. Look at me. 278.15 Kelvin. We're looking for the V2. What is the new volume the gas would occupy if the tank leaked? Uh-oh, something that we would not want to happen, right? So let's see. Thank you, Sina. All right, thank you. 298. All right, so now we're going to plug in looking for V2. So guys, remember what I said, right? If you look at this formula, you are going to solve for V2. That means these 3 numbers are given and divide by the other 2. All right? So here we go. I'm going to go down here. Let me put it like this. Okay? I'm going to squeeze this in right here because we're looking for V2. P1 times V1 times T2 divided by P2 times T1. All right, so P1, 150 atm. V1, 2.0 liters. T2, 278.15 Kelvin. Divided by P2, 0.7 atms. Times T1, 298.15 Kelvin. Y'all know what to do. Strike out the units you no longer need so you know what's left over. Okay? So let's zoom in so we can see those numbers. And what I'm going to do is multiply everything across. And then divide by everything on the bottom. And we get 399.8. So we're just going to round that off to 400. 400 is your V2. All right? 400 liters. Now, if you all think about these numbers here, okay? If you think about it, there was a lot going on, right? There was a lot going on within this problem. So you all just have to be mindful, and let's plug it in and make sure 150 ATMs times 2.0 times 278.15 divided by 0.7, then divided again by 298.15. Yep, 299.8, roughly 400. Okay, 400 liters. All right. So guys, when you all are doing these examples, just work with the numbers you were given and plug them in accordingly. All right. Work with the numbers you were given and plug them in accordingly. Now, I know we've been talking about these gas laws, and I keep seeing a lot of stuff in the comments about the ideal gas law. Now, let me say something about the ideal gas law.